And Dr. Katherine Auld will be talking about the Voyager mission. How long have you been a Solar System Ambassador?
4 years.
4 years. Okay, great. Well, I know you've done a ton of work. I know you're very, very active. You teach astronomy.
Yes.
You are involved locally in Northwest Arkansas for setting up a science center too. So, you know.
That's the goal.
That's the goal.
That's the goal.
Anyways, I'll present Dr. Katherine Auld and let her get started.
Great, thank you. So today I'm going to be talking about the history of the Voyager missions. It's one of my favorite missions just because they started so early and they're still going. So in 1965, Gary Flandroy was working at JPL, and he was working on the Mariner missions, and working on trajectory for Mariner, and realized that a single mission in the 70s could launch from Earth and pass by all 4 of what we now call the outer planets. And from Neptune, they could do a trajectory adjust and also pass by Pluto. And so he said, hey, this would be a lot cheaper than sending a mission to each of those planets individually. Let's do this. And so the idea was that we would do the grand tour. The problem was that the mission was going to cost, around $750 million to $900 million, plus another $100 million to launch the 4 spacecraft. So the mission was going to be 4 spacecraft, 2 to the inner 2 to Jupiter and Saturn, 2 to Neptune and Uranus. They would take 1 each of a Mariner-like spacecraft, and then 1 each of a brand new spacecraft, and launch those. The first set would go in 1977 to Jupiter and Saturn, and then in 79 they'd go to Neptune and Uranus. And so this is an image of the brand new spacecraft that they wanted to design, with many of the same kinds of instruments that we have on the Voyager missions. They just were going to do some improvements and arrange them on the spacecraft a little different to protect the radiation detectors from the RTG. RTG is radioisotope thermoelectric generator. And so those will interfere with the results of many of the science experiments. The problem then being, going back to that money issue, $1 billion to build 2 new spacecraft and launch. At the same time, we were working on the space shuttle program. We also had the Viking missions that we were trying to finish building, spending a ton of money on Viking, and the Apollo missions that were costing around $1.2 billion each. So Congress said, cut some money, and because of that, the last 3 Apollo missions were canceled. The Grand Tour mission was canceled. And so instead, we had this idea, okay, let's not build new spacecraft. We already have the 2 Mariner-like spacecraft that were almost completely built. Let's just take those 2, launch them, and by only visiting 2 spacecraft, a bunch of that $1 billion was 10 years worth of tracking the spacecraft and keeping up with the science. So if we shorten the mission down to only 4 years, save a ton of money. Now we're only looking at $360 million. So this was approved in 1972. And they started working on the trajectories. So JST was the name for the first mission, and it was Jupiter, Saturn, Titan. And so the spacecraft was going to launch, visit Jupiter, Saturn, but it was going to come in to Saturn from the pole and swing across the northern side of Saturn and view Titan on the way past. And then JSX was Jupiter, Saturn, and something extra, basically, is what the X means. It was designed so that if the first mission was not successful, they could do the exact same thing. If the first mission was successful and we already had great images of Titan, then we could go on and look at Uranus and Neptune as well. And so, you know, like many things with NASA, we design them and say, we want this to work for 90 days. And 14 years later, it's still working. So that was the hope, but we didn't know how well that would work. And so then just a couple of months before launch, NASA decided, because these spacecraft are now so very different from the Mariner spacecraft, because we've changed quite a few of the instruments on them, they need a new name. They need their own name. So they held a contest, and Voyager was the winner. So March of '77, they announced the new names. And Voyager 2 actually launched first in order to maintain that trajectory of being able to hit all 4 of the planets in a row. They had to launch before, they had to launch Voyager 2 before Voyager 1, actually.
We weren't really sure what you guys were doing, but
So, then on September 5th, Voyager 1 launched, and because it was a faster spacecraft on a faster trajectory, it actually arrived at Jupiter first, started out 2 weeks behind and showed up 4 months ahead, so it caught up a bunch of time, and then arrived at Saturn 9 months ahead of time. And so Voyager 1 launches on September 5th. September 6th, so less than 24 hours later, it's already 7.25 million miles from the Earth and takes the first photograph ever of the Earth and the Moon in the same photograph. So we're going to talk about lots of discoveries and lots of firsts, because this mission has lots of those. Am I moving around too much?
It's okay. They want me to zoom in a little bit so they can read the slides better.
Oh, okay.
Mm-hmm.
So we both missions launched, and so then Jupiter, March the 5th, Jupiter arrives, or Voyager arrives at Jupiter. I'll move over so we can, and that's supposed to be a GIF, and it's not
rotating.
Okay, cool. So the things that Voyager 1 discovered during its visit to Jupiter. On Io, it discovered that there are volcanoes on the surface. We never knew that until this mission. It was the first time that we realized that ions get stripped off of the surface of Io and end up in this cloud. It's called a torus, a donut-shaped cloud around Jupiter, and they add to Jupiter's magnetosphere. So they make its magnetosphere even stronger than it should be. The other thing is that Io acts like a generator within Jupiter's magnetosphere, and 5 million gigawatts of energy transfer from Io to Jupiter every year. That's a lot of energy. Some other things that Voyager discovered was the fact that Jupiter had rings. Everybody knew that Saturn had rings, but until about 2 months before Voyager arrived at Jupiter, we did not realize that Jupiter had rings. Voyager discovered 2 new moons on Jupiter, Thebe and Metis. and discovered that the red spot, everybody had been seeing the red spot for 100 years, well, more than 100 years, but seeing that the red spot is actually a cyclone, basically a hurricane, and it spirals. The other thing that Jupiter saw for the first time was lightning on another planet. So lots of firsts for Voyager 1. Wow. That's not supposed to go that fast. But anyway, so Voyager 2 then arrives at Jupiter 4 months later. It's coming in from a slightly different angle, and because we've already discovered that there's rings, now we direct it to actually look at the rings, and we get the first photographic images of the ring system. Voyager 2 discovered another moon, and during its close approach to Europa, discovers that there are cracks in the ice. We knew that Europa was very bright and assumed already that it was ice covered, but we got close enough to see that there are cracks in the ice and that it looks like those cracks are moving. This gives us the idea for the first time that Europa had liquid water under that ice core or ice shell. And then we also discovered that 6 of the volcanoes on Io that were erupting when Voyager 1 went past were still erupting when Voyager 2 went by. So the idea that volcanoes could continue for that long, this is 4 months later, continue that long on a moon was a new realization for scientists everywhere. Then we continue moving on out. Saturn. Voyager 1 approaches Saturn in November of 1980. Once again, it's the first time we've had a spacecraft near these planets, so lots of discoveries. 3 moons. We got the first view of many parts of the rings on Jupiter. The fact that F is not a flat ring like most of the other ones that have sort of a homogeneous texture. F looks like there's strands. It almost looks like a braid. And so being able to see that for the first time, we got to see the very bright surface on Enceladus, which immediately made scientists think back to Europa and the fact that it's bright and frozen. And then we got our first images of the atmosphere on Titan. Titan was a point of interest from the beginning because of the fact that we thought it looked like it had an atmosphere. And so we got close enough to figure out, oh, that atmosphere is very rich in nitrogen. And we have images that suggest that there were methane and ethane seas on the surface. So once again, lots of firsts. So many things that were discovered in these missions. And so Voyager 1 trucks on out and heads out of the plane of the solar system. It's sort of up. And Voyager 2 shows up 9 months later. Highlights for the Voyager 2 mission, close encounters with several of the moons. And we discovered that on Enceladus, some of the surface is rather smooth with no impact craters, and some of it is covered in impact craters. In geology for Earth, that would mean that some of the surface is very old and some is very young. So this once again gives us evidence that there's movement in those plates of ice on the surface of Enceladus. We think it's geologically active. And then the other thing from Voyager 2, as it was flying near the northern portion of Saturn, we took images that were later stitched together.
To speak more this way.
All right.
Okay.
That were later stitched together to show the hexagonal wind pattern that we see on Saturn that Juno mission is currently exploring. And so Voyager 1 is headed up and out of the solar system. We won't see much more in the way of space or planets from, well, we won't see anything more of planets from Voyager 1. But Voyager 2 continues on to Uranus, discovers 11 moons, discovers that the poles of the magnetic field and the poles of the rotational field are tilted almost 90 degrees from each other. So we're still exploring what could have happened in Uranus's history to cause that huge shift. Uranus has extremely dark rings. We got some great images. They're very hard to see from Earth because they're so dark. From here, in order for us to see something in telescopes, we need it to be bright and shiny. And the rings are dark, so we can't see them. Temperatures on Uranus drop down to 59 Kelvin, which doesn't mean much to most people, but if I say negative 353 degrees Fahrenheit, that's super cold. It's actually the coldest planet in our solar system. And because Uranus is so far away from the sun, this was actually the first time that the Deep Space Network, which is our big listening telescopes that are antenna that we use to listen for the spacecraft. This was the first time that they had used multiple telescopes together to amplify their listening ability so that they could actually hear from the spacecraft. So we're headed on out, and because they were having such a hard time hearing the message from Uranus, they knew, oh my goodness, we're gonna have to get bigger antenna. So all 3 sites on the Deep Space Network were expanded, and we noticed that each one of the sites basically covers a third of the sky coming out from the Earth. So even though, we think antenna, I can see from here to here, we really do cover a third of the Earth with each one of those. But in 1987, the antenna were extended from 64 meters to 70 meters. So that's a huge antenna. One of these days I'm going to go visit one of them. And now we've finally gotten out to Neptune. So now we're all the way up to 1989. Things that we discovered. 6 moons. Discovered that Neptune as well has the great dark spot. It's another storm cycling counterclockwise on the surface of Neptune. We have first images of Neptune's rings. Well, by this time we had figured out a trend. Okay, Jupiter had rings. We knew Saturn had rings. Neptune has rings. I bet Uranus has rings too. And sure enough, they did. And we got images of them. And then we got images of Triton, which is a weird moon with surface that's all crinkly and looks like the surface of a cantaloupe. And they actually call it cantaloupe texture. So then Voyager 2 heads out from the solar system, sort of just below the plane of the planets. In first October and then December of 1989, the scientists turned off the wide angle and then the narrow angle cameras on Voyager 2. It was never going to see another planet, and they could use that power to prolong the mission if they just completely shut down the cameras for forever. And so there's no picture because there's going to be no more pictures from Voyager 2. We'll see a couple more from Voyager 1. And here is the set of pictures taken from Voyager 1 from 6 billion kilometers away from the sun. Various different images. You got pictures of all of the planets in our solar system. Shortly after this, the cameras on Voyager 1 were also shut down to conserve power. And so now we have spacecraft trekking out from the solar system, one moving basically up and one down from the plane of the planets. So in February of 1989, Voyager 1 surpassed the Pioneer 10 as the object that was now the farthest away from the sun, any man-made object. Voyager 1 will forever be the fastest moving, well, I shouldn't say forever. It is currently the fastest moving man-made object, even though New Horizon launched with a much higher launch speed. The gravity assists that Voyager 1 got from mostly Jupiter, but all 4 of the planets, made it now the fastest moving object that we have launched to date. It is leaving our solar system at 3.6 astronomical units per year, which comes out to several, like 10 or 12 miles per second, which is just crazy. So in December 16th of 2004, we actually lost an opportunity. This was the point where Voyager 1 crossed the termination shock. So we have this bubble that the sun makes around itself and makes a fairly calm space in space. All the planets are in here. And the termination shock is this edge of the calmness. And you end up out here in the heliosheath, which is fairly turbulent. When Voyager passed the termination shock, that day the antenna were actually listening to Voyager 2. And so we have no data from the actual day that Voyager passed it. We just know that the next time we looked at Voyager 1, the data was completely different. And so we learned our lesson. We knew approximately when Voyager 2 from when Voyager 1 passed, we knew about when Voyager 2 should be crossing the termination shock, and we spent a lot of time focused on Voyager 2 so that we actually have data of the time when Voyager passed through this termination shock. And that was out in, 2007. So they launched 30 years before they got to the edge of the beginning of the edge of our solar system. Voyager 2 launched two weeks before Voyager 1. So on August 13th, 2012, it became the longest continuously operating mission in history. Surpassed Pioneer 6. On this day, it had been operating for 12,758 days. And so I got curious, and today is 14,996 days of continuous operation, which I say means in 4 days we need to have a party. So then, August 2012, Voyager passed the heliosheath. The edge of the heliosheath is called the heliopause. When we're talking about atmospheres, every layer in the atmosphere, the outer edge of that is called the something pause, the mesopause, the stratopause, in this case, the heliopause. And so Voyager 1 crossed the heliopause August 25th of 2012 and became the first man-made object in interstellar space. At that time, it began receiving a full measure of cosmic radiation, but we weren't certain that that was actually interstellar space for several more months. April 9th of 2013, the sun had a CME, a coronal mass ejection, which basically means that a bit of the sun explodes out into space. And those masses, those particles, travel very fast and very far. And so that CME went so far that it passed through the terminal shock, through the heliosheath, through the heliopause, and struck Voyager 1. When they did, they made all the plasma around it ring. And the tone that the plasma was vibrating with gave us a sense that the density is 40 times higher than what we anticipated, and proved that Voyager 1 is actually in interstellar space, not still in our solar system. And so now we are in what NASA calls VIM, NASA loves acronyms, Voyager Interstellar Mission. And the spacecraft have enough electrical power to continue sending data back until at least 2020. And so the estimate is that at that point, Voyager 1 will be 22.1 billion kilometers from the Earth, and Voyager 2 will be 18.4 billion kilometers from the Earth. And so from now until then, we will continue to study the character of the plasma and all of the particles that they are collecting out there in space. So, questions?